Okay, so today we are going to discuss on primarily two techniques, encoding techniques, because right now we are aware of what is prefix code, how they are termed as a prefix code, the basic properties of a prefix code, what is Crafts inequality, all this we know. The one thing that we don't know, that you might question me, that sir, the last day when we were doing it, that for the given set of symbols and given set of probabilities, I was just writing on some code words as per my wish. The zeros and ones, whatever the combinations are, and the length of those codes were all given by me. So the two techniques that we are going to discuss today will actually give you the process to form those code words. Okay, the length of the code words, how will it be 2 bits or 3 bits or 4 bits or even more, that can be given by two methods. In which the first one is called as Shannon's binary method. So the first method is called as Shannon's binary method. We will also find that if possible we will finish off with the Shannon Fano technique also, but let's start with Shannon binary method. We will solve a numerical which will give you an idea about how to process with this, but just for the time being let us write the rules for doing this method. Okay? So the first rule is write down the probabilities in decreasing order. So the first point is, we will do problem, but these are the rules first. The first is to write down the probabilities in decreasing order. Whatever the number of symbols, whatever be the probabilities, just arrange it. Second, which in most cases will be given in the order. So this first step will be taken care of by the question itself. Second is, so we might write here itself, px1 should be greater than px2, like that it will go on till p of x of m. So like that we can write. Second rule is, compute the sequence. This is where it is very important. Compute the sequence as alpha 1, or maybe we can write alpha naught. It's better to write alpha. Okay. Alpha naught is equal to 0. Alpha 1 is given by p of x1. See how I'm doing it. Alpha 2 is p of x1 plus p of x2, or p of x2 plus alpha 1. Alpha 3 will be p of x1 plus x2 plus x3, or p of x3 plus alpha 2. So this is how we are going to compute. We are partitioning. There is a reason for doing it. So these are the rules. So you have to compute this sequence. Now why we have to do it? That we have to find along with that. So rule number 3. Determine. Just write it for the time being. We'll solve it. Clarify. Determine the set of integers set of integers which is smallest integer solution of the inequality to the power minus LK. Maybe I will write this. P of Sk, or the probability of the symbol, should always be greater than equal to 2 to the power minus Lk. Okay, so this is a condition you have to fit. Just write it. I will explain it, everything. And the fourth point is expand the decimal numbers alpha k, that is the one that we have done, in binary form to Lk places. So these are the 4 rules. First, we have to make it, the order should be in the decreasing order. Then we have to do the process. Let's take an example. Okay? This is where it all holds true. Let's have a scenario. We'll go one by one. Let's have the 4, we have 4 symbols. So X is given by X1, X2, X3 and X4 with the probabilities as 0.4, 0.3, 0.2 and 0.1. So the first step, it is mentioned that the order of the probabilities are given in the order of decreasing order. So the first step is already done. If it is not given, you have to rearrange. That's why the rule comes in. But in most of the problems, you will find that the order will be like this. So you don't have to waste your time. So you have this. The question is to find out, using Shannon's binary technique, find the code words. That's how the question will be. So find the code words. Find the code word and efficiency of the code. Also find the redundancy of the code. All these numericals will have these 3 components: code word, redundancy and efficiency. So all these are common. So even if I don't write, you have to find them. So we have this. So what we are going to do is we will first do that classification using alpha. So the first thing what we are going to do, we will have, so if I write step 1 is already taken care of because this is already the step 1. So step 2 is alpha 0 is equal to 0, alpha 1 is equal to 0.4, alpha 2 is 0.4 plus 0.3 equals 0.7, alpha 3 is 0.7 plus 0.2 or 0.9. We will not take the last sample. Please remember this. We are not taking this one. That we are not adding 0.9 plus 0.1. We are not doing that. Last sample, because we have already taken one sample here. We have a reason for it. So just focus on, we will box this alpha equal to 0, alpha 1 equal to 0.4 just for our own convenience, and alpha 3 equals to 0.9. Now the third step, check for the inequality. So step 3. So we have to check P of Sk if it is greater than 2 to the power minus Lk, where Lk is the length of the code word. Okay. So we have to find the process. So we will take, for example, we will take 0.4. First symbol has the probability 0.4. Please understand this. Now, what will be the value of Lk such that this inequality holds. That is the condition. So you have to make something so that 2 to the power minus LK, this condition holds. So what will be the value of L, which is the length of the code word, so that this condition holds? Can you tell me? If it is LK equal to, and as it has been already told that LK should be, K should be, okay, I think I have missed there. K, what is the value of K? K should always be 0, 1 to K minus 1, or the total number of symbols, M minus 1 in this case. So if suppose I take L equals to, LK equals to 1, because that is the minimum symbol, the code word I need. So if it is 1, so it becomes 2 to the power minus 1. So half. Right. So what I am asking is, let LK equals to 1. Okay. So your condition becomes 0.4 is whether it is, I don't know whether it's greater than equal to 2 to the power minus 1. So this is half. So this condition doesn't hold. So LK cannot be 1. So the next higher integer it can take is 2. So we will go and take it 2. So 0.4 greater than 2 to the power minus 2. Now this is 1 by 2 square. So 1 by 4, which is 0.25. So your answer is coming as 0.4 greater than 0.25. Hence the inequality holds. So we can assume that LK or L2, if I consider this one, as 2 bits. I don't know about it, how many, the 2 bits can be multiple combination, 1, 0, 0, 1, 1, 1, that is separate. But at least we know that for the symbols, the first symbol at least, for probability 0.4, the length of the code word should be of 2. Can you find me the other 3? For probability 0.3, suppose P of S2, which is 0.3, what will be the condition? What will be the value of LK? What is the value of L such that this satisfies? Can we take 1? No. Can we take 2? Yes, we can, because if we take L equal to 2, it's still coming 0.25. 0.3 is greater than 0.25, hence it satisfies. So for this also, L2, if I let this be L1, okay, this be L1 because this is the first symbol. So this becomes 216. What about P of S3, which was 0.2? So will it be L equal to 2 in this case as well? What will be the value of L? 3, because 1 by 2 to the power 3 is 1 by 8. So that satisfies. So this is 3. And naturally P of S4 is 0.1. So what will be the value of, in this case? Will 1 by 3 match? 1 by 2 to the power 3? No. So it should be 4. I am repeating once again. What I did, we have to satisfy this particular inequality. P of probability of individual symbol should be greater than equal to the 2 to the power minus LK, where LK is the code word duration for each of those probabilities. We are not looking at the combinations, we are just finding the length. So from there, to satisfy this condition, for the first case 0.4, it can only be greater than equal to 2 to the power minus LK if and only if LK is supposed to be 2. That's a minimum value. 3, 4, we can go for it, but 2 is also giving us the answer. We will always take the least number of bits. As we all know, the more lesser we can take, the better is the efficiency of the system. So naturally, we will take that. So 0.4 is satisfied with LK equal to 2. Similarly, we did for the other probabilities. So the third step is done. Now the fourth step. Fourth step, what was it mentioned? Fourth step was mentioned as expand the decimal numbers of alpha in binary form to LK places, right? So what we are going to do is we will just convert a decimal to binary conversion. So let's take step 4. So alpha naught is 0. So this is what the value of alpha naught is. So we'll convert that to binary, which happens to be the same. So 0, 0, it will be all zeros. If we convert that to binary, naturally. How do you convert that, any decimal number to binary? Multiply, divide by 2, or if it is a factor, like in this case 0.4, what will it happen? Suppose for alpha 1, it's 0.4. For fractional value, what you do? Multiply by 2. Yes, that's correct. So first we'll go for 0.4 first. We'll see what we are doing. Alpha 0 is 0. So this is my decimal number. Even if we convert that to binary, it will be all zeros. So these are all zeros. See, I have written dot dot dot. Why I have written dot dot dot? I'll take only LK values. So for alpha naught, the values of L should be only 2. Because you can go here, the first length is giving us value of 2. So I'll go for the decimal to conversion to binary, but we'll go till 2 places. So your value for alpha naught will be 0, 0. Now if I convert, can anyone give me the answer for what will be the binary conversion for 0.4? So we'll do this way. I'll just show it for once since we are starting. So this is how we do it. 0.8. We take the 0 out. So again 0.8 multiplied by 2. So it's 1.6. We take the 1 out. 0.6 multiplied by 2. So we take 1.2. We take 1 out. 0.2 multiplied by 2. So 0.4 we take the 0 out. Like that it will go on. So your code for alpha 1, if I write, in terms of binary number, it should look something like 0, 1, 1, 0 and rest of the things. That's how to do it. This is nothing but ITC from digital electronics. So you get the alpha 1 as that form. But why I have stopped with 4 points? Because the length that we are looking at is only 2. So we have to only focus on this 2 length. So from this I get 0, 0. From the next time I get 0, 1. Can you compute for the third one? Where alpha 2 was given by 0.7. Can anyone give me the exact answer for this? 0.7. If it is this way, in binary if you convert that, at least alpha 2, if you write this way, give me the length that you are getting. 1, 0, something, a few more bits. 1, 1, okay, let me write this. Again, how many bits we have to consider? 3 bits, I guess. So, we take these 3 bits. What will be alpha 3? Alpha 3. When you convert that, so it is coming almost like 1, 1, 1, 0, 0 and rest of the things you convert. For alpha 3, how many bits we need to consider? 4. So if I write a new table, symbol, probabilities, maybe length, and now comes the code word. So your symbols are x1, x2, x3, x4 with probabilities 0.4, 0.3, 0.2 and 0.1. What are the 4 lengths? Just give me 2, 2, 3 and last one 4. So you go back to alpha 0. This is 2. What are the 2 bits? 0, 0. So substitute over here. For alpha 1, this is 0. 2 bits were there. 0, 1. Or it is 0, 1. 0, 1. Correct. 0, 1. For alpha 2, because this is what we have taken. 3 bits. So 1, 0, 1. So 1, 0, 1. And the last one is 4 bits. So 1, 1, 1, Now you can observe this happens to be a prefix code once again, by the property that it is not repeating itself in any of the code words. So it's a prefix code. But now you can determine that why for x1, x2, x3, x4 the code words will look like the double zeros or 01 or 10. This is what I was giving it to you last day. But now we know how to form this. That is what the source encoding technique is. We are encoding it with some code words. Is it clear with the process? I'll give you a longer sequence. Let's see whether you can do it or not. Fine. Up till now, this point, any doubt? We have to check the 4 criterias and we have to come up with this. Okay, let me finish off with this problem first. Can you find me h of x source entropy, because we have to find the efficiency of the code as well as the redundancy. So can you find me hx for this? So hx will be nothing but p of xi log base 2 p of xi with a minus summation I equal to c 1 to m or 0 to 1 to m. So this is my normal source entropy. So drop in the probabilities, calculate and tell me the value of hx. So 0.4 log of 0.4 plus 0.3 log of 0.3 plus 0.2 log of 0.2 plus 0.1 log of 0.2. That is what we do. Just tell me the answer, because we will do in a different way. Answer this. H of x. People on the back. Hx. Just find hx. That's really simple only. 1 point. Everyone agrees. 1.846. Please participate. 846 bits per symbol. Now, can anyone give me L average? What was the formula for L average? Pk multiplied by Lk summation. Take the individual probability, multiply it with the corresponding length of the code word. Not the code word, length of the code word. So 0.4 multiplied by 2. So 0.4 multiplied by 2 plus 0.3 multiplied by 2 plus 0.2 multiplied by 3 plus 0.1 multiplied by 4. So this is your summation Pk multiplied by Lk. This gives you the average length, average code word length, and that comes out to be 2.4 bits per symbol. Now, just to add on to this, I told you that L should always be, or L average should always be greater than equal to h of x. That's Shannon's theorem. So you can just check for yourself that whether your answer is correct or not. So the L average is greater than what the hx is. So that's one of the, suppose the question demands that prove the Shannon's first theorem or Shannon's theorem. So you can actually verify it from here itself. Okay, that's one thing. Now, as far as the efficiency, coding efficiency is concerned, eta, that is given by h of x given L average. H of x divided by L average. So this is given by 1.846 divided by 2.4, and this is coming around 76 in percentage you have to find. Because it's an efficiency, always efficiency is expressed in percentage. So it's almost 76%. And your redundancy, sorry, 1 minus eta, so it is 1 minus 0.769, which is around 0.231 or around 24%. If you convert that in percentage, it will come out. All these numericals will have the same thing. You will be given a set of symbols and you will be given a set of probabilities. From there you have to come with the code words as well as coding efficiency and redundancy. Please note down this efficiency for the time being. What I will do is I will finish off with the Shannon Fano also. Then we will take one single example and we will compare for two. Okay. Let's finish off with Shannon Fano because that's more simpler compared to this. Shannon Fano will take this example itself. So ideally, what I'll do is I'll go to the numerical directly. Okay, instead of giving the rules, maybe I'll just give you the question itself. That's better. Let's take the same example. Okay. So Shannon Fano is what we are doing. Because the detailed rule and all is given in the notes which I'll be uploading, so you will get it there itself. So it's better to solve numericals rather than giving for this. So this is called as Shannon Fano. The earlier one was Shannon's binary code. Now this is called as Shannon Fano. What we are going to do is first we'll write the symbols which is x equal to x1, x2, x3 and x4. Please, if you have doubt, tell me, because these are all very important for your exams as well as for Cat 1 as well as your government. So be very specific. I won't get time to come back to this once again. So just stop me if you are having any doubt. Again, the first rule is to have the order in the decreasing order. So 0.4, 0.3, 0.2 and 0.1. Suppose this is already made in order. So no need to do it. The question is to find using Shannon Fano the code words, the efficiency of the code and the redundancy. So it's the same question. What we are going to do is, we will arrange the probabilities in this manner. So 0.4, 0.3, 0.2 and 0.1. Now, we will divide the probabilities into sets such that the summation of the elements in each of the set is almost equivalent. That is what they say. That's the rule. I'm telling you, you don't have to write. So basically, we have to divide these probabilities in such a manner in two different sets, such that both the sets have the total sum probabilities almost equal. So how do you divide this? How can you divide this two? If you ask me, one can be 0.4 plus 0.3 and the other, so one I can segregate like this. So 0.4 plus 0.3 is 0.7, the other one is 0.3. So 0.7 and 0.3, they are not equiprobable at all, they are very different. So maybe we can do one thing, if I take it here, naturally it won't happen. 0.3 plus 0.4 plus 0.3 plus 0.2 will definitely be much greater than 0.1. So only thing is possible, I think it's this. If I keep it 0.4, and I make it 0.6, the rest half. So it is still not equal, but at least close enough. So what I'll do is, I'll rewrite it once again. So 0.4 partition 0.3, 0.2 and 0.1. So all these three are in a group. So this is basically your set x2 and this is your set x1. Understand? We are dividing the whole probabilities into two sets of almost equiprobable. If they are equiprobable, naturally it will be better. But if not, then we have to find the closest possible. So this is one of the closest. 0.4 is the upper one. Next half is 0.6. So this is what we have done. Now, allot ones and zeros to each of the sets. So I'll allot 1 and zeros to this set. So what will it look like? So it will look something like 0, 0 and 0. It can be other way around as well. You can put 0.4 as 0 and 0.3, 2 and 1 to be 1, 1, 1. And that's also a possibility. It will be remaining same except for the code will differ. I'll do that problem as well. Maybe next day we'll solve that. So this is my first step. You will go on dividing into these sets until and unless each set contains only one element. That was rule number 2. So you can see x1 we cannot divide it further because it already has one element. So we cannot go beyond, but we can divide this one. So your next step is, if I consider this to be the step 1, so step 2 is, we'll keep this as a null because we are not dividing anything. We will divide 0.3, 0.2 and 0.1 into 2 different sets. So maybe we can write 0.3 partition 0.2 and 0.1. See, they are equiprobable once again. So at least in this case they are equiprobable. Since they are now the 2 different sets, make sure one is having 1 and the other 2 are having 0s. Am I clear what I am doing? So again, I will stop here with this one 0.3 because it is only one element in this set. So we cannot go further. So it is over. So step 3 will only have 0.2 which is the element 1. So we will put at 1 and 0.1 to be element as 0. I will repeat it once again. What I did first, we rearrange the probabilities into decreasing order. We will divide it. Maybe I'll just do one thing. Wait. I'll just remove this line. Then it will be easier for you to understand. So what we are going to do is, we are going to divide the probabilities into 2 sets in which the summation of the sets will be almost equiprobable, if not equiprobable. So we are dividing this one as this pattern and we will go on dividing this until and unless each and every set contains only one element. Whenever we are giving these 2 sets, one of the sets will be given 1, the other sets and the elements on this set will be given 0. So we are giving the second set of the x2 as 0, 0, 0. Since the first set x1 we cannot break it into any other further, we are giving a dash in that. Whereas for the x2, that also can be divided into 2 sets. So because of multiple elements, we don't have any single element. So we are dividing that into 2 halves once again. Since we are giving the upper half as 1, we are mentioning upper half as 1. So the upper half of 0.3, we have mentioned it as 1 once again. Whereas the bottom half, we are given 0, 0. So step 3, where we are going, in that 0.3 cannot be further reduced. So it remains as it is. But 0.2 and 0.1 are further reduced to 1s and 0s. Because in that also 0.2 becomes the first element of the set and 0.1 becomes the last element of the set. So 2 sets again 1s and 0s. Now see, if I want to write the tabulation once again, so you have symbols, you have the probabilities, you have the code. Now I will write the code here because length we haven't found anything as of now. So symbols are x1, x2, x3 and x4, whereas the probabilities are given by 0.4, 0.3, 0.2 and 0.1. Can you tell me what will be the code for x1? We are going to go here. x1 has ended over here. So this is my x1. Only 1, then dash and dash. So we don't take any value. So the value is 1. So the code for this becomes 1. I'll write it with a different color maybe. So it's 1. For 0.3, step 1 had 0. Second step had 1. Third step we don't have anything. So 0 and 1. So your elements are in this case as 0. For the x3, we have x2, we have the first step as 0. Second step we have 0. Third step we have 1. So 0, 0, 1. And as far as 0.1 is concerned, anyone? Correct. So you have 0, 0, 0. See the easy way in we are trying to find the code words as respect to Shannon's binary technique. Is it not more convenient to find it? That's why Shannon Fano finds its more importance compared to Shannon binary. Now, if this is the case, can you quickly write the LK or the length of the code word? So in this case is 1, 2, 3 and 3. So naturally your HX will be same. So this will be 1.84 something you found out, 84 bits. This is what we found out last in the last problem itself. Can anyone give me L average? Can anyone just give me the L average for this? .7, 1.9, somewhere you have made a mistake. So it's like 0.4 multiplied by 1, 0.3 multiplied by 2, 0.2 multiplied by 3 and 0.1 multiplied by 3. Okay. So L average should come around 1.9 bits per second. Again the condition satisfies that L average is greater than equal to LHX. So that is also satisfied. So can anyone give me the efficiency? Efficiency calculation, HX by L average, it should come around 97%. Now if you compare with the earlier problem, what was the efficiency? Shannon's binary 76. So as far as the coding efficiency is concerned, from 76 to 97 we are achieving, okay, with respect to this technique. This particular process is known as Shannon-Fano. Also, you can find the redundancy actually. So 1 minus eta will give you redundancy of around 2.85%. Something like that. Is it fine with the Shannon binary and Shannon-Fano technique? How we are going to solve it and all? This is applicable if anyone follows the other way around. Can you do it for me? Can you give me the code word for this? I don't have it here. So can you do it with respect to keeping the top half to be 0 and the rest half to be 1? Can you give me the code words? Because otherwise it will be same. Just give me the code words. Yeah. Okay, good question. This is a very good question. What he is asking is that if it is 0.3, 0.2, 0.1, why can't we take 0.4 and 0.1? What will be the fundamental problem with that? The order of probabilities will not be available. That's the first rule. The order of probabilities should always be in the decreasing order. So you cannot change that. If you want to 0.1, then the order will be 0.4, 0.1, 0.3, 0.2. So it violates the condition itself. So it's not applicable. Can you give me the code word keeping the top half to be 1 and the rest half to be 0? Huh? Top half to be 1. In this case, what we have considered, the top half to be 1. Rest, the bottom half we have considered 0. I am asking the other way around. Do this as 0 and this as 1. The rest is 1. Yes. It will be just opposite way around. So just I want the code words. Right? Now can you do it using Shannon-Fano, this particular problem? Let's see whether within this time you can able to solve it. We have symbols given as maybe x as 0.03, 0.2, 0.1, 0.07, 0.4, 0.2, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay? These are the possible probabilities of symbols. Symbols x6, x2, x4, x5, x1 and x2, x3. These are the respective probabilities of the not so much in order for the symbols with the given probabilities. Use the Shannon-Fano technique in order to find what are the code words. I would say take the first half to be 1 and the rest is 0. Take that as a approximation just for the timing. Let's see whether you have understood that. 0.402 The first step is to rearrange it. So arrangement is not there. So arrange the probabilities properly. x1 to x6. Then the partition. So these are the arrangements of the probabilities. How will you divide the two partitions? Which one is favorable? One you can do is something of this nature. You can keep 0.4 as one element and keep rest of the things as one. But ideally, if you take this, how many partitions do we need after this? You need a partition after this. Like 0.2, 0.2, 0.1. So this is, will the second partition be almost equally probable if you consider this? Let's see. If I take 0.2, 0.2, it's 0.4. What is this value? This is 0.2. No, I'm taking the second step. Suppose I have taken this as a first step. Step 2, I have to partition this half, right? The second half. This I have to divide. So if I take 0.2 alone and the rest together, it's not equally probable. Nearest, even if I take 0.2 and 0.2 together, and then that is 0.4 and the other one is 0.2. So that's also not equally probable. So one option is, the better option rather in this case, is instead of taking 0.4, you take this half. Because you see, why this is a possibility. The other one is also there, but you have to understand this. See, when we are going for the second half, this is 0.2. I can keep that as 1. Okay? Okay, from here, 0.2, and here you are getting 0.2 once again. Step 2 will be 0.2, 0.1, 0.07, 0.03. So if you partition here, it's basically coming as equivalent. Okay. Again point? Yes, 0.4 and 0.2. Okay. Wait. See, there is a little confusion regarding the partition, I guess. What I am asking is to have the partition of this nature. Why I am doing this? Because ideally this is the only option that we have to make sure that the second partition, this partition at second step, will come to a same equiprobable condition. That is the only reason. Now if you argue that 0.2 and 0.4 they are far apart, I'll take that into consideration only because this part is mapping with us. Please take this as a condition. There is no strict rule. You can follow the other way around as well. But ideally, if you take this and you put 1 and 1 over here and zeros for all the other elements, so this is only 2 elements here. So will you stop partitioning the first half? Because you have 2 elements. So again you have to partition. So your 0.4 will be 1, whereas 0.2 in the second step will be 0. But at the second step, this needs to be partitioned once again. So 0.2 partition 0.1, 0.07 and 0.03, where we will keep this as 0, 0, 0 and this as 1. Simultaneously. It is supposed to be simultaneously. I am doing it part by part. Like you have to do it because this partition doesn't exist anymore. Only at the first step you are doing the partition. After that, when you are going to second step, you are basically calculating on the basis of what partitions you have made already. Okay. So here when you are reaching 0.2 and 0.4, now they are all single elements. You don't have to worry. 0.2 also has single element. You don't have to worry. So your third step will involve 0.1, 0.07 like this. So we'll continue from this maybe. Okay, we'll take another example where we compare the Shannon Fano and Shannon binary.